Welcome to KF5012 Software Engineering Practice Week 4. This is the Artificial Intelligence stream. I'm Dan, and I'm going to take you through neural networks, deep neural networks, and all the kind of different offshoots, or some of the different offshoots that come with neural networks. There's far too many to go into all of them, but I'm going to take the rest of this course through from week 4 through till week 6. This lecture, I'm going to really do a thorough introduction of neural networks. So I'm going to start off just explaining to you the power of neural networks and how they've completely revolutionized the field of artificial intelligence in the last decade. And I'm also going to give some instructions on how you can set up an environment locally on your own machine to do some coding, to do some experimentation. So this will also work with the machine learning stuff you've seen in the first few practical sessions, but it's especially important with neural networks. Then I'm going to get into the bulk of the main lecture. I'm going to start off mostly talking about the limitations of neural networks. Even though they're incredibly powerful, there are still some things that they don't do too well, and there are some challenges that you need to be aware of when you are coding them and when you're deploying them. So I'm going to go into those. I'm going to give an overview of vectors, matrices, and tensors as well for those of you that are less familiar with the mathematics. Then finally, I'm going to explain what a one-layer neural network looks like. And I'm going to give a simple example with such a shallow neural network. Finally, we're going to move on to the deep networks, and I'm going to show you how they work and try to give you an intuitive understanding of what's going on. Even if we can't fully understand what's going on, I'm going to try and show you the sort of ideas to give you a conceptual understanding of what's happening within these networks. So a couple of things before I move on. Firstly, this obviously isn't being delivered face-to-face, it's not being delivered live, so I think that gives me a bit more flexibility with how much I can deliver. So you've got buttons to speed this up to 2 times speed. You've got the ability to skip a little section of the video if you think what I'm talking about is too obvious or too easy. So what I'm going to do, for those of you that maybe are more new to this and want to go into everything in full detail, I'm going to provide all of that detail. And if you want to skip over little bits because it's too obvious, then you're going to have the option to do that. The flip side would be if I didn't do that and just skip through things and some of you didn't understand, then there's no kind of button on YouTube for you to poke me and say, go into more detail here. There's not been an AI created yet that can do that. So I'm going to, when in doubt, I'm going to give a little bit more detail. But feel free to skip ahead if you're getting a little bit too bored by me going in that much depth. The other thing, I'm going to try and cover as little maths as possible. This is more of an application course rather than a theoretical course. So because we're interested in practically being able to work with deep learning, we don't need to know the theory that much. So the maths isn't as important. If you want to go more into the maths, there is a mathematical background mission. And I'm very keen for you to explore the maths on your own time, but to actually deliver the projects yourselves, you don't necessarily need that maths to do them beyond some of the basics like the vectors, matrices, and tensors video. Lastly, I'm going to try and do a lot of scribbling. I think, personally, I don't like just looking at slides on a YouTube video. I like something which is going to move about a bit more and is more engaging. So please give me some feedback on this. Let me know if you can read my writing. Let me know if you do find it more engaging and more interactive, and if it helps your learning. So I'm going to start off by going into this paper, which is Imagenet Classification with Deep Convolutional Neural Networks from 2012. And I'm not going to go straight into the details of the paper, but I want to show you these results. And this is the turning point for artificial intelligence. Since this paper was released in 2012, the interest in AI has skyrocketed. And the reason for that is because this paper proposed deep convolutional neural networks and got massively improved performance on these big competitions. And since then, everyone's dived onto this idea of using deep neural networks, and across the board, you just see much better performance on pretty much any task that you use compared to the traditional machine learning tools. So in the initial 2010 competition, you had this sparse coding paper, which actually won the competition with an error rate of 47% and a top 5 error rate of 28%. And in the 2 years following that, lots of different traditional machine learning techniques were used. The best was this combination of sift features and Fisher vectors, and they managed to reduce that from 47.1 to 45.7 in 2 years. Again, the top 5 error rate, it was just a 2.5% reduction. Then this paper comes along with convolutional neural networks and completely obliterates the field. You get a improvement of 8% on sift and Fisher vectors on top 1 and on top 5% performance. And on the 2012 competition, you see something very, very similar. On the test sets, they perform pretty much 10% better compared with the sift and Fisher vectors. This star just means they used a bit of additional training data, so it's a slightly different result, this 15.3%, which is outside the scope of the competition. But yeah, it just shows that you can improve it even further with these deep CNNs. And this trend moved forward throughout the next 5 to 10 years. And you can see just in this kind of 1 year, you're already getting this massive performance boost. But by 2013, with deep networks, we managed to get another 5% off. And then 2014 gave another 5%. And then we get to the likes of ResNet, and in 2017 squeeze and excitation networks, which are down from an error rate of 16.4% to an error rate of 2.3% in the space of 5 years, which is really, really incredible. And a lot of the performance gain that you get is to do with the ability for these networks to get deeper and deeper. So ResNet in particular has an option to go not just for 5 or 10 layers, but you can get much deeper than that. So there's a ResNet which is 18 layers, and then I'd say the most popular ResNet architecture at the moment is 50 layers, but then there's options to do 100 layers, 151 layers. You can get really, really deep with these networks, and as long as you've got enough data, then that's going to be beneficial. And of course, this isn't true just for image categorization. We see a performance boost pretty much across the board with lots of different tools where you might, lots of different tasks where you might use deep learning. You'll see this a lot if you look at survey papers where they have this specific red dotted line to say, hey, this is where we first saw deep learning, and you'll often that red line will be accompanied by a massive performance boost from 2012 to 2013. So you can see here for object detection with 20 categories, before deep learning is really proposed, you have this kind of plateau where we get to about 40% mean average precision, and you can't really do any better than that. In like that whole year, no one could improve upon it. Suddenly, deep learning comes along. In 1 year, we go from 40% to like 55%. Then we're above 60%. And suddenly, we're above 80%. It's really, really incredible. And you can see that since deep learning has become a thing, now we're not really worried too much about 20 categories, but we can do 200 categories. So there's 200 different types of objects that we're trying to detect. And they didn't, because their performance was so bad in 2011 on just the 20 categories, they didn't even bother trying to go for 200 categories. You can see in 2013 they're only getting 20% mean average precision. By 2017, they're already up to 25%. It's really incredible how good these deep learning architectures are at scaling up performance. So the reason for this is that as you get deeper and deeper, the features that you learn become a lot more powerful. So one of the problems with the traditional machine learning stuff is that you're required to essentially design and extract features manually, right? So this feature extraction process is done pretty much by humans. And what neural networks are going to do, the main difference from neural networks to other machine learning classifiers, is that neural networks learn the optimal features themselves. So we're taking humans out of the loop. I'm going to talk about this in more detail in a future video, but one of the things that deep learning actually allows us to do is it gives us a lot more flexibility. So you think about how much social media has exploded. Twitter in terms of text data, or like Instagram, Snapchat, TikTok in terms of visual data. We're creating so much more data every day than we were in the first like millions of years of human existence. We just simply can't rely on humans to design features for all of the specific possibility, like all of the specific data types that we have. No one's gonna, like, unless people are really, really passionate, they're not gonna design a specific feature for a specific type of, say, hippo, and then you need someone else for a different type of hippo. What deep learning can do is learn all of these features automatically, and the deeper the network gets, the more expressive those features are going to be. So they themselves can differentiate between the different types of hippo. So what has this done for deep learning, not just in the academia bubble, but within the real world? You can see that deep learning is receiving a massive amount of hype, and this hype starts around 2014 and goes up massively from there. So generally industry and the real world is going to be a few years behind academia, and you'll see if you look at the number of papers that have machine learning, you see a similar trend, but it's a few years earlier. But it's safe to say that there's loads and loads of people that have now become interested in deep learning, and when you come to look at jobs, this is becoming a more and more important skill. So you'll see that 76%, this is an article from Forbes that I read a few days ago, 76% of enterprises are actually prioritizing AI and machine learning in 2021. So hopefully when it comes to applying for grad schemes, there are a lot of software engineering firms that are now retraining their software engineers to be able to do AI and machine learning. And a very large part of that is deep learning because it just gets better results. So this course should put you in a fantastic position to get a job when you finish it. In particular, the next few lectures, if you do your project on deep learning, if you do your final year project on deep learning, you should be in an amazing position to find a grad scheme off the back of that. So I really encourage you to think strongly about what sort of project you're going to do. If you want to start a business, you can see the trend from 2015 to 2019 of how much money is being invested in artificial intelligence. And again, this is all coming off the back of the success of deep learning in academia. And you can see that just in the second quarter of 2019, this is up to $7.4 billion. So if you're interested in starting a business, this is a massive opportunity for you. And even further from that, you can see the number of patents that different companies are generating from 2010 to, again, 2019. And you'll see that back before deep learning, it was mostly Microsoft that was generating most of the patents. But since 2013, there's been a lot more interest from a lot more different companies. And you can see now that people like IBM and Samsung are generating a large number of patents as well. And then there's all these other companies that have gone from basically 0 patents to thousands of them. And then lastly, the global machine learning market. Again, you see similar trends, but this is forecasting to 2024. And you should see again that this course is going to put you in a fantastic position to get a job because there's just so much more demand for machine learning and deep learning in industry. So let's talk about deep learning and how deep can a network get. So this is a graph that you'll see very commonly in natural language processing papers, which explores the number of parameters that a model can learn. And we're already in the kind of billions of parameters stage over here. This paper that was proposed last year actually scales up to 1 trillion parameters. So there's 1 trillion things that this model is learning, which is really exceptional and pretty extraordinary. I would say don't worry too much about that. We're not going to go that massive in this course, but this just gives you an idea of how crazy this is starting to get in the past year or so. But in general, you see this trend that the deeper your model goes, or the more parameters that your model is learning, the lower the test loss is going to be. And you see that pretty consistently. As you get more parameters, your loss is going to come down, as long as you've got enough data and as long as you aren't overfitting. There's one big problem with that though, which is how expensive in terms of computation these models are going to be. So I'm going to show you now this state-of-the-art model on Imagenet Classification. So we've come a long way since 2012. We're now using this VIT Huge, which is the current state-of-the-art, is using 32 transformer layers. So these are more advanced than the fully connected layers I'm going to talk about in this lecture. I'm going to talk about transformers in lecture 6, but this is a comparatively modest 632 million parameters compared to the paper we saw on the last slide. But just to talk about the time it takes to train these networks, which is a big limitation of deep networks. Most of you will have heard of a CPU, and those of you who are very interested in gaming might have your own GPUs as well. So deep learning models are usually trained on GPUs, graphics processing units, because they're more powerful than CPUs, and that's using a library called CUDA. Now, from graphics processing units, Google have actually developed their own tensor processing units, which are specifically designed for machine learning, or for deep learning, I should say. And what this paper is saying is if you've got one of these tensor processing units, which are state of the art and cost thousands of pounds each, if you've got one of those and you're going to train their model on this, it's going to take 2,500 days to train. So to get state-of-the-art results on ImageNet, you need 2,500 days and already a lot of money. So what they're doing is probably using 100, maybe 1,000 of these TPUs and using them all at the same time to train these models. Now, that obviously isn't going to be possible for us because we don't have the same resources as Google does. We're not going to be training models as big as this, but what I am going to show you is how to use GPUs for free using Google Colab, and this should be more than enough computation power to train anything that you want to train for your projects or as part of this course.